In our last video at Eigen Academy, we took a deep dive into solid angles, and today we are going to continue from there on. Before we get into today's main discussion, let's revisit the two problems we left for you to try at the end of the last video. We are going to walk through them now, both of which rely heavily on the concept of solid angle that we had developed earlier. First, the benzene tank problem. We were told that a point source is placed at a depth h below the flat surface of a tank filled with benzene. The refractive index of benzene is given as 4/3, and the source emits light in all directions, but because of total internal reflection at the light-air boundary, only a limited cone of light escapes. The rest, hitting the surface with an angle greater than the critical angle, suffer total internal reflection and get trapped inside. The diagram should make it very clear how that works. To find out how much power remains trapped, we first calculate the critical angle by using Snell's law, which is the formula used to describe the relationship between the angles of incidence and refraction. Now that would give us the half angle of the escape cone. And then we use the solid angle formula for a cone, which is omega equals 2 pi times 1 minus cos theta c, to determine what fraction of the full sphere is actually escaping. And we multiply that with the total power to find out how much light gets out, and here we see that that is equal to 20.31 watts. And we simply subtract that from the original to get the trapped power, so we had the original power as 120 watts, and thus this gives us 99.7 watts as the final answer. Next, we move on to the electric field line problem. This was a conceptual one. We were given two charges, plus q and minus 2q, placed at points A and B. Now, a field line originates from plus q that leaves at an angle alpha, and it ends at minus 2q, entering at some angle beta. And the question asked was, what should the angle beta be equal to ensure continuity? Here we use the idea that electric field lines behave like flux, and thus the concept of continuity of flux, that is, the flux through charge plus q, is the same as the flux through minus 2q. In fact, let's solve this generally first. Equating the flux leaving through q1 to that through q2, we get omega 1 over 4 pi times q1 by epsilon naught equals minus omega 2 over 4 pi times q1 by epsilon naught. The minus sign appears since flux is leaving q1 while it's entering q2. After this, we use the cone solid angle expression again, and thereafter we simplify this expression. The easiest way to proceed is by using the trigonometric identity 1 minus cos x equals 2 sine squared x by 2. Now, after some substitution and simplification, we are going to get sine beta by 2 equals the square root of q1 over minus q2 times sine alpha by 2, the arc sine of which gives us beta. Now q1 here equals plus q and q2 equals minus 2q, and substituting these values gives us the final answer, which is beta equals the sine inverse of 1 over square root 2 times the sine of alpha by 2. And thus we are done solving the two problems. Both of these problems beautifully reinforce the utility of solid angles, both in geometrical optics and electrostatics. Now that we have developed a fairly strong conceptual base on solid angles, it's time to move ahead with our discussion on units and measurements. So far, we have looked at units as standards of measurements, and here on we are going to look into some aspects of measurements without the knowledge of which the measurement becomes utterly meaningless, just as it does without its units. We'll divide the rest of this video into uncertainty in measurements, significant figures, and how errors propagate. These are all extremely essential for doing physics correctly and are often misunderstood or ignored. So, what is uncertainty? Any physical measurement we make has to come along with the knowledge of its uncertainty, that is, the range within which the true value is likely to lie. Suppose we measure the thickness of a book with a ruler and get 3 millimeters. Is it really 3 millimeters? Not quite. The real value could be 2.85 or 3.11 millimeters. We simply don't know. Now, we can use a vernier caliper and get 2.91 millimeters with much finer resolution. Both of these are measurements, but the second one has a lower uncertainty. It's more precise. Similarly, you can think of something as simple as measuring your own height with a metal scale. While standing against a wall, your height might read something like 174.3 with an uncertainty of plus minus zero point 0.1 centimeters, which is the least count of the scale. But if you lie flat and try again, you might get something more like 175 centimeters or so, as your spine is no longer compressed due to gravity. So you see, this variation isn't due to some sort of mistake, rather it reflects the natural uncertainty in the measurement. Now, there are different ways to express uncertainty, and so we look at some of the types of errors in numerical analysis. First, we have absolute error, which is the difference between measured and true values and is given as delta A equals modulus of difference between A measured and A true. Next, relative error describes how large the error is compared to the actual values, and this is given as delta A over true A. Finally, we have percentage error, which is simply the relative error times 100%. Now, a point to note is that even if the absolute error of a measurement is tiny, it is not guaranteed that the percentage error is also small. In fact, what may at first look like a good or convenient absolute error to your eyes can result in an enormous percentage error if the true value of A is also small, and you can see that right here in this demonstration. In this graph here, the true values of A are represented by the x-axis, while the y-axis shows the percentage error. And you can see as we go to lower values of A true, the percentage error just blows up. In fact, with a little bit of luck, well, good or bad is up to you to decide, you might be able to see this in the experiments in your first year physics lab or thereafter at your future university. Say, for instance, while performing an experiment to obtain Planck's constant with faulty equipments, and thus you may obtain Planck's constant off by several powers of 10. You would be surprised to hear this is something that happens in real life, sadly even in premier institutes. Lakhs in tuition fees well spent, I suppose? Jokes aside, this distinction becomes critical in high precision measurements like in quantum physics or electronics. Sometimes, uncertainty may not be explicitly stated. In such cases, we often infer it from significant figures. Simply put, these are the meaningful digits in a number, and there are a few basic rules we follow to determine how many significant figures a number has. So now, let's look at these rules to figure out how it all works. First, non-zero digits are always significant. For instance, let's take 28.66 meters. all the 4 digits here are significant. What can we say about the uncertainty here though? The last digit, being in the hundredths place, it's 0.01 meters. How about 286 kilometers? It has 3 significant figures, and its last digit being in the units place, it has an uncertainty of 1 kilometers. Now, the second rule states that the zeros between the non-zero digits are also significant. Let's take 201.506 as an example with a certain unit. So here you can see that all the zeros are sandwiched between non-zero digits. Thus, we have 6 significant figures in this case. This brings us to the third rule, which states that leading zeros are not significant. These are the zeros that appear before the first non-zero digit of a number. For instance, if we consider this example, the zeros before 5 and 2 in the number 0.0052. And thus, here you can see that there are only 2 significant figures, that is 5 and 2. The zeros only act as placeholders and do not give us any information about precision of the instrument. As for trailing zeros, they are significant if they occur after a decimal point, as in that case they do reflect precision in measurement. So if you have, say, 3.400, there are 4 significant figures, as the zeros after the decimal are meaningful in measurement. Now you may ask, how about trailing zeros in the case of whole numbers? Well, in general they are insignificant, but sometimes they may require more context. For instance, what about that 10 that comes before the decimal point in 340.0? Or what about 340 that just comes with a decimal point? Or simply 340? While the second example here is not an usual convention in writing numbers, when it's written that way, it is to imply the significance of the trailing digit. Trailing zeros in a whole number with the decimal shown are significant. So 340.0 has 4 significant figures, while 340 point has 3, and simply 340 has 2, as trailing zeros in a whole number with no decimal shown are not significant. In fact, to clear ambiguity surrounding the number of significant figures when trailing zeros appear, it is best to use scientific notations to provide clarity with additional context. So 1.5 times 10 to the power of 3 has 2 significant figures, while 1.50 times 10 to the power of 3 has 3 significant figures. Thus, in scientific notation, only the coefficient determines the number of significant figures. Now, what about numbers that act as definitions rather than measurement? Say we have 1 meter. So, these exact numbers have infinite significant figures, as they do not limit precision in calculations. So by definition, 1 meter can be written as 100 centimeters or 1000 millimeters and so on. So it has an infinite number of significant figures. When you measure 1 meter though, say using a meter stick, without decimal precision and obtain the length rounded to the nearest meter as 1 meter, then it has one significant figure. Or if you use a measuring device with precision up to millimeters and obtain 1.000 meters, that has 4 significant figures. Yet, when we write something like 1 meter equals 100 centimeters, where it's a conversion constant or a definition, there are infinite number of interpreted significant figures. I hope that this is very clear to you, especially the fact that the number of significant figures reflects the precision of the instrument, not just the number itself. Another rule for significant figures, which is actually more advanced and better suited to higher studies in chemistry or physics dealing with pH or decibel levels, has to do with logarithmic quantities. So say you have log 3.45 times 10 to the power 2, While you may calculate this as 2.5376, that is not the correct way to express it. The number of significant digits in the original number is 3. So when expressing the log in decimals, it should have 3 decimal places, so we have to write that as 2.538. Similarly, log 4 with one significant figure should be written as 0.6 and log 4.000 with 4 significant figures as 0.6021. Thus, we have covered all the rules for significant figures, and here you can go through them once again before we move on to the next topic. Now that we understand how to count significant figures, let's talk about what happens when you perform calculations with them, since when we compute using numbers having uncertainties, the resulting numbers are also uncertain. First off, whenever you multiply or divide quantities, the final answer should have no more significant figures than the number with the fewest significant figures in the input. For example, say 0.745 times 2.2. 0.745 has 3 significant figures while 2.2 has 2. 2 being the smaller of these two numbers, the final calculation should also have 2 significant figures. So we multiply to obtain 1.639, rounded off to 2 significant figures, and thus this gives us 1.6 as our final result. The same goes for division, and you can try this out for yourself. If you have 3.14 times 1.2 divided by 36.9, you should end up with 0.10. So we've seen how it works for multiplications and divisions. On the other hand, when dealing with additions and subtractions, we aren't concerned with the number of significant figures, rather the decimal places. Basically, we are supposed to round off to the least precise decimal place. Say we have 217.1536 plus 1.382 minus 11.74. This equals 206.7956. But the least precise decimal place among the values involved is the hundredths place in 11.74. So we round off to 2 figures after the decimal, ending up with 206.80. Hence, when you divide a given circumference by diameter and end up calculating something like 3.14149 or something, you should remember to round off based on the precision of the inputs. For example, if a millimeter tape has been used to obtain these measurements, and you have something like 424 millimeters over 135 millimeters, you'd be working with 3 significant figures, thus obtaining 3.14070741, which you round off to 3.14. For a larger circle, where you measure 5512 millimeters over 1755 millimeters, you'd end up with 4 significant figures, giving you 3.142 and so on. So you see, this doesn't have to do with accuracy of measurement, but the precision, the limitation of the measuring instruments. I hope that this is clear, because accuracy and precision are often confused with each other, so it's best to clarify now. Accuracy refers to how close a measurement is to the true or accepted value. Precision, on the other hand, refers to how consistently a set of measurements agree with each other, regardless of whether they are correct. A measurement could have both high accuracy and high precision when the true value is reached consistently, like hitting several darts close to the target. Or it could have a high precision but low accuracy, akin to how you can consistently hit darts very close together, yet far away from the bullseye, so it's consistent but wrong. Similarly, you can have low precision with high accuracy, where the average may be right, but the measurements vary, like these darts which are circling around the bullseye. And finally, of course, there's the case of low accuracy and low precision, where neither consistency nor correction is attained. In fact, let's take a few numerical examples and see if we can figure out correctly. So in the first case, we see that the measured values are very close to the true value as well as precise. So both accuracy and precision are high. In the second case, while the precision is high, accuracy is low as the value is far off from the true value. Same goes for the third case. And finally, in the fourth case, we can see that both accuracy as well as precision are low. And if you obtain something like this at the lab, your teacher might ask you to do the experiment all over again. We'll now explore how these uncertainties propagate when we perform operations like addition, multiplication, or exponentiation. We already saw while studying significant figures that we often don't stop at measuring just one quantity, we calculate other values from them. While we are familiar with the rules of how significant figures affect calculations, thus far we were quantifying uncertainty in a single measurement. Yet most physical results are derived from not a single quantity, but combinations, especially in the case of dependent quantities like area, density, and so on. So let's look at how error itself propagates when we do the math with uncertain quantities and how this affects the final result. So in case of addition and subtraction, absolute errors add up. For example, say we have A equals 5.0 plus minus 0.1 centimeters and B equals 2.0 plus minus 0.2 centimeters. If we calculate Z equals A plus B, we get Z equals 7.0 centimeters, and as for delta Z, it's 0.1 plus 0.2 or 0.3 centimeters. That's because in the worst case scenario, A is 0.1 too high and B is 0.2 too high, so the full error in Z is the sum of the two. And thus Z would be written as 7.0 plus minus 0.3 centimeters. In case of multiplication or division, the relative errors add up. So if we consider the same example of A and B as before, then we can see that the uncertainty in A is 0.1 times 5.0, which is 0.02 or 2%, and for B it's 0.1 or 10%. So the relative error in Z is the sum of these two, which equals 0.12. This is delta Z over Z. Thus, delta Z is 0.12 times 10, that is 1.2, and this gives us the final result as you can see here. Finally, when we deal with exponents or power functions, the relative error is multiplied by the power. So if Z is given as a to the power of n, delta Z by Z is the modulus of n times delta A over A. Say A equals 2.00 plus minus 0.05 and Z equals A squared. Then the relative error in Z is twice 0.05 by 2.00, which is 5%. The error doubles as squaring amplifies any fluctuation. This last rule actually comes from calculus. The derivative of a to the power n is n times a to the power n minus 1, and so small changes in the base lead to scaled changes in the output. So in essence, these rules help ensure that your calculated results carry uncertainties that reflect the quality of your measurements, a central goal in experimental physics. So let's quickly recap what we covered in this video. We began by discussing two conceptually rich problems based on solid angles, one dealing with ray optics and another with electrostatics. Then we explored the idea of uncertainty, and we moved on to types of errors, then covered significant figures and how to handle them during calculations, and how uncertainty propagates through mathematical operations. In the next episode, we move on to dimensions, dimensional formulae, and dimensional analysis, where you'll learn how to extract deep physical meaning from the units themselves. If time permits, we'll look into deriving Planck's units using dimensional analysis, and we can also look into how dimensional reasoning played a role in estimating the energy of the Trinity nuclear test as originally done by G.I. Taylor, which is a beautiful example of power of units in the real world. So stay tuned and make sure you've subscribed to Eigen Akademie if you haven't already. Thanks for watching and see you in the next video.